Good evening and happy Wednesday. As I always say, right, technology is great until it doesn't work. Hopefully we don't have another Teams hiccup this term. So I did post the videos for the finding zeros of polynomials, the rational functions, as well as variation. Excuse me. So we're going to move on to Unit 3, which is exponential and logarithmic functions. All right, so let's start by examining logarithmic function. Or not logarithm, I'm sorry, exponential function. So we're going to take some positive real number b such that b is not equal to 1. The function b raised to the x is called the exponential function base b. Regardless of the base, always going to have domain of all real numbers and range of positive real numbers. We'll have a horizontal asymptote at y equals 0. Has no x-intercept. And I'll have a y-intercept at 0, 1. Again, these are true regardless of what the base is. So two of the most common bases used in mathematics. Right, we have b equals 10. This is called the common base. In fact, our decimal system is base 10. However, there is a base that is used more often in mathematics than 10. That's called the base E. Called the natural base. Right? E, approximately, 2.718282. And of course, this is transcendental. This number will go on forever with no discernible pattern. The actual definition of E is this. Now, the idea of a limit you study in Calc 1 is very similar to end behavior. In fact, it is end behavior if you let n go to infinity. Okay. All right, so what we're going to do for the first set of problems. Okay, why is this zoomed out? That's kind of annoying. There we go. Perfect. Okay, so we will go ahead and analyze the exponential function, sketch its graph, and then we will look at the actual graph as provided by a graphing utility. And again, domain, all real numbers. Range will be positive real numbers. Okay, so 0 is going to be 1. That's the y-intercept. Has no x-intercept. Has a horizontal asymptote, y equals 0. I haven't thought that far ahead yet. I'm probably going to make it available the first day of finals and have it due the following day. Now, here's the question. Horizontal asymptote. Which side? Right, because it doesn't have to be both sides. Right. So, in other words, what we want is end behavior. So what happens as we let x continue to increase? Right, so we get 2 to the first power versus 2 squared, right? Versus 2 cubed versus 2 to the 10th, 2 to the 100th, 2 to the 1,000th. That also gets larger, doesn't it? So as x increases without bounds, so does f of x. Right, so 2 to the x is just going to keep getting larger and larger and larger. However, if x is getting larger in the negative direction, right? So 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, 2 to the minus 10, 2 to the minus 100, 2 to the minus 1,000. They start to approach 0. There's our horizontal asymptote. All right, so let's say that is 1. There's negative 1. 2 to the minus 1 would be 1/2. Say there's negative 2. 2 to the negative 2 would be negative 1/4. So I'm sorry, positive 1/4, so on and so forth. All right, 2 to the first power is going to be 2. 2 to the second power, and it's going to be 4. So maybe something like that. Right, so I think it's tools, right? No, it was window. No, it wasn't. Screen capture, it's right there. Oh, good grief. Oh, it looks pretty good, right? Okay, so what about 2 to the negative x? But I definitely agree it's going to be reflected about the y-axis. What is the base? So to be base 2, it would have to be 2 to the x. Right. So it'd be base 1/2. Because you can write it as 1/2 to the x power, right? Remember, right? M raised to the -1 is the same as 1 over m. Domain is still all real numbers. Range is still all positive real numbers. F of 0 is still 0. Still have horizontal asymptote, y equals 0. Now, since we know it's being reflected about the y-axis, we know that the end behavior switches roles. Right. But does that make sense? Right. So 1/2, what happens when you take a value less than 1 and start to raise it to positive powers? And so a 1/2 squared versus a 1/2 to the 10th, right? Versus a 1/2 to the 100th. It will start to get smaller, specifically to 0. And it's not like dividing it. I mean, we are dividing it, right? So a 1/2 squared would just be a 1/2 divided by 2, because remember, 1/2 times a 1/2 is the same as 1/2 over 2. So you keep cutting it in half with each power. But on the other hand, if you let x start to get large in the negative direction, right? 1/2 to the negative 2, 1/2 to the negative 10, 1/2 to the negative 100. Well, if you treat it like 2 to the negative x, then that 1/2 to the negative 100 is like 2 to the 100. Right? A 1/2 to the negative 1,000th is like 2 to the 1,000. So it keeps getting larger. Specifically, it'll keep increasing without bound. We're going to probably do something like that. And if I come up here and adjust, actually I want to do it this way. Let me turn that off. And do that. Apparently that was f sub 9. That's interesting. Well, whatever. So let's go ahead and get this in here. And so again, that looks pretty good. Now let me turn on that as well. All right, just so I have both graphs together. And indeed, as expected, they are mirror images of each other across the y-axis. Possibly my favorite application of exponential functions is the idea behind exponential growth, right? So compound interest. The idea is fairly straightforward. What we will find is that the amount of money you have in an account at some time t is equal to P naught, your initial amount in the account, also known as your principal, times 1 plus rate of growth, yearly rate of growth, divided by number of times per year that your interest compounds, then raised to the nt. Let's rewrite that. So important to note that R has to be in decimal form. And this problem, we are asked to consider the principal amount of $1,000. Rate of growth, rate of return is 5% annually. We want to calculate how much we're going to have after 7 years if the account compounds in 5 different numbers. So first, yearly. Well, yearly compound, sorry, n would just be 1, wouldn't it? So we want P of 7. We know P naught's 1,000. 1 plus the rate of return in decimal form divided by 1, all raised to the n, which is 1 times 7. Be 1.05 raised to the 7th power, then multiply that by 1,000. $1,407.10. Quarterly compound. So if it compounds quarterly, then how many compounds in 1 year do we have? 4 of them, right? P of 7 would be 1,000 times 1 plus 0.05 divided by 4 raised to the 4 times 7. .05 divided by 4. I believe that's 0.0125. And then 4 times 7 is 28. Oh, joy. $14.15.99. right? If we compound monthly, how many compounding periods do we have? P of 7 would then be 1,000. 1 plus 0.05 divided by 12 raised to the 12 times 7. And that'll wind up being 1,000 times 12.05 divided by 12 raised to the 84th power. $14.18 and 4 cents. Are you sure about that? How can you have a quarter of a day? Right, but that doesn't mean in a given year you have a quarter of a day, right? Uh-oh. Why did my screen just disappear? I have no idea why it just stopped sharing. No, still no. Okay, so I'm gonna have to do this. Oi, what's going on? Okay, so let's try and rejoin. Perfect. Share. Perfect. And we're back, apparently. That's nice. So extra day every 4 years. That is not entirely correct. Okay, so there are 3 rules for a leap year. If the year is divisible by 4, it is a leap year. Unless it is divisible by 100, then it is not a leap year. Unless it is divisible by 400, then it is a leap year. So the year 3000 will not be a leap year. But the year 4000 will be. Okay. This presents a problem. Right? Because you can't have a quarter of a day in a year. So most years, it'll be 365. Some of the years, it'll be 366. Oh, but that's also assuming that it truly does compound every day and not just banking days. Right, which some accounts do. Some accounts will only accumulate on banking days, which are Monday through Friday and not holidays. Well, be careful because businesses tend to be open on holidays. We are going to make a very simple assumption that it's just going to be a straight 365. Because even if we take into account leap years, how many leap years are in our 7-year period? Could be 1 or 2. We don't know. So for our purposes, we would just take it to be a straight 365 days. And then 7 times 365, 2,555. $14,1903. So if we had a compound of annually, right? So compounds annually. How much total interest did we gain in the 7 years? $47.10. What if it compounded quarterly? How much total interest was gained? Does that make sense? Why? Okay, but why is there more money? Because the initial investment was the same, 1,000. Because it compounds more often. Exactly. So interest, so you gain interest. Then the next time that interest is calculated, you're gaining interest also on the interest that you just gained, right? That's why it's called compound interest. So every time interest is calculated, every time your account compounds, you gain interest on what is currently in the account, including any interest you've already gained. And then you can see that the monthly you've gained more interest, and then the daily you've gained even more interest. So doesn't that kind of mean that effectively the interest rates are different? Right. So that is the idea of an effective interest rate. Right. The rate itself is not, but effectively it's different. Right. So that's what effectively means, right? So an effective interest rate is what the annual interest rate would need to be to gain the same amount of interest in a single compound. Right. So compound annually, your effective interest rate would just be, in this case, 5%. Now, if it compounds quarterly, your effective interest rate is slightly larger than 5%, right? Because you're going to gain more interest. So effectively, your rate of return for that year was larger than 5%. See that? Because you only put in 1,000. Now if we have continuous compounding, what is N? Right, so be careful, N is not infinity because infinity is a concept. Right? It tends to infinity, right? Well, that's a problem. But that is where my definition of E comes in. So remember, we had our formula was P of T, which equals P naught times 1 plus R over N raised to the N times T. This tends to P naught E to the R times T as N increases without bound. All right. Unfortunately, without the concepts of calculus, you just have to take my word on that. I can't actually prove that right now. But once you've studied the idea of limits, which is the first thing you study in Calc 1, you'll be able to easily derive this. So for continuous compounding, our formula is P of T equals P naught E to the RT. That means for this problem, after 7 years, we have $1,000. E to the 0.05 times 7. Right, that's 1,000 times E to the 0.35. Now, when you're doing calculations with E on your calculator, you do not want to use the approximate value of E. You want to find the E button. Which is right there on the TI Inspire. It's red on the screen. And then just hit enter after that. 141907. There's another way you can do it with the Inspire. You can also just type out EXP parentheses and then what E is being raised to the power of. So EXP is the natural exponential function command. Right, and it should, if once I enter, it should convert to E to the 0.35, which it did. See that? So either way. So when you're picking a savings account, there are two things you want to keep in mind. The rate of return, right? Because obviously a higher rate of return means more interest. But you also want to look at how often does it compound? Right? Because obviously, the more times we compound, the more money we get. So this problem was to show you that you want to keep in mind the number of compounds. What the next problem is going to do for us is show us another important feature. Hi, buddy. Hi. Say hello. Okay, now say goodbye. Go get mommy. Yeah. So we're going to be investing $6,500 into an account that earns 12% interest that compounds annually. We're going to see how much money we have in the account after 5 years, after 10, after 20, and then after 50. Right, so a little background on this problem. Are you familiar with the idea of IRAs? or 401ks, right? 404Bs, 414Hs, right? Retirement accounts, right? So IRA is called an individual retirement account, so that's outside of work. Then there's something called a Roth IRA or a Roth 401k. Right? Do you know what a Roth account means? And so the difference between a Roth retirement account and a non-Roth retirement account. Right? It's a subtle difference. It's a very slight difference that has a huge impact. So non-Roth, which is what a standard 401k is, money goes in before taxes are taken out. Roth is after tax. Right? So traditional is just before tax dollars. Roth is after tax dollars. Now, here's where that slight difference makes all the difference in the world. With a traditional account, when you withdraw from it, you have to pay income tax on it. It goes as part of your income. I'm talking federally. Each state is different. Each state has its own income tax laws, but for federal income taxes, traditional, whenever you draw out, you pay an income tax on it. It goes towards your annual income. With a Roth, you do not pay any federal income tax. You pay 0 federal taxes when you withdraw, even on the growth. That can make a huge difference, as this problem is going to show. If you're currently enrolled in a 401k, 404B, 414H, some kind of retirement account at your work that's not a pension, ask if they have a Roth option. That is your best bet. Now for this problem, Roth IRA, and I think even traditional IRA, so outside of work, as of this year has a $6,500 annual limit. So you can only invest $6,500 a year into an IRA. Up until age 55, at which point then you can do 7,500, an extra 1,000. Right? Or was it an extra 500? I think it might actually be an extra 500, so 7,000. Let me just double check that. It is an extra 1,000. It's after age 50. Okay. So 6,500 a year up to age 50, and then an extra 1,000 after that. %, annual rate of return. You can easily find mutual funds that do this. So keep in mind, I'm basing this off of an average rate of return, right? Because obviously, anyone who follows the stock market knows that last year the stock market was down like 20-something%. But the previous years it was up like 20-something%, right? So over the fund's lifetime, you can easily find things that average 12% over its lifetime. So that's what I'm basing that interest off of. In fact, all my accounts average over 12% return per year. So I'm basing this to show you why you should probably start investing as soon as you're able to, which is 18. Right, so I'm assuming 18-year-old does one deposit of $6,500 into an IRA, pick good funds that average 12% per year rate of return. We're going to see, okay, after 5 years, how much do they have? After 10, after 20, and then after 50, which would be age 68. So since we're doing annual, right, we're going to have P of T equals 6,500 times 1.12 raised to the T. And I'm going to do this straight up on here. So let me just go ahead and clear the sketch pad. If you're working with a TI and SPI, you can actually store functions, which is what I'm going to do. So I'm going to say P of T is defined as, so colon equals, $6,500 times 1.12 raised to the T power. I'm going to hit enter. You'll see it now says done. That means this function is now stored. And now if you notice, if when I type in P, it's now bold. So that means I'm recalling a stored value. P of 5. So after 5 years, $11,455.22. Now keep in mind that there was only a single deposit of 6,500. So how much of that is growth? Slightly under 5,000. All right, so for simplicity's sake, let's just say it's $5,000. If this was a Roth IRA, no federal taxes on any of that, even the growth. Next up was what? P of 10, right? 10 years. So after 10 years, $20,188.01. So it almost doubled. So let's look at P of 20. $62,700.91. More than tripled. in those 10 years. P of 50. So what do we think? From 5 to 10, it about doubled. From 10 to 20, it looks like it tripled. So what about from 20 to 50? Try 7 figures. After 50 years, you have about $1.9 million in the account. And again, if this was Roth, that's $1.9 million federal tax-free. So what you did was pay taxes on the $6,500, right? Because remember, Roth is after tax. So you pay taxes on that $6,500. You have $1.8 million in growth that you pay 0 taxes on. Okay, let's have some fun. So let's say you decide you're going to work until age 70. So that's an extra 2 years. You have about $2.3 million. And then let's say you decide you're going to work an extra 5 years, so you're going to go to 75. You now have 41.5 million. Something doesn't seem right. No, that's not 41.5, is it? No. That is. It is 41. Oh, yeah, I guess it would be. Okay. Now, again, this is assuming a single deposit of $6,500 and no withdrawals. Just imagine how much more money you'd have if you actually contribute the maximum every year. The point of this problem was to show you the other factor when you're dealing with savings or compound interest. And that is the power of time. Time is your best friend. The longer you leave it in there, the better. Right? While it's never too late to start investing, the best time to start is as soon as you're able to. I think what I'll do is go up to here. I don't know why I'm doing this. This isn't available for you, but there's no way that 57 should give me 41 million. So let's simplify some expressions that involve exponential functions. And so remember, with exponents, raise a fraction to an exponent. That exponent is distributed to both the numerator and the denominator, right? And remember, since we have a common denominator, we can just subtract the two numerators. I'm going to expand out this first numerator here. And so I have e to the 2x plus twice their product. So what is e to the x times e to the negative x? How did you get E? What do you mean by cancel out? Cancel out would have two meanings, right? Either 0 or 1. X to the minus 1 is 1 over x. A negative exponent just takes the reciprocal of the base. No, negative x is not the reciprocal of x. X to the minus 1 would be the reciprocal of x. E to the negative x would be the reciprocal of e to the x. All right. The product would be e to the x minus x, right? Multiply same base, you just add the exponents. Remember that? But that would be e to the 0. What's e to the 0? Just 1. So twice the product would be 2. And then plus e to the negative 2x. You can expand out the second term. E to the 2x minus twice their product. And then plus e to the negative 2x. So numerator, we're going to be left with what? 2 minus negative 2, right? That's just 4. This simplifies down to 1. Well, you should look at the numerator here. Isn't this numerator the exact same thing we did up here? And we got it to be 4. So no need to reinvent the wheel. That's just 4. Expand this out. We're going to have except I actually don't want to do that here. Do I? No, I don't want to do that here. Technically, we'll just leave it alone. And expanding it out serves no purpose. And I would be okay with this. I'm going to add a stipulation. I'm now going to say you can't have negative exponents in the denominator. So in the denominator, factor out an e to the minus x. Right? We're going to be left with e to the 2x plus 1. But remember, that whole thing's being squared. Now, if you take a product raised to a power, you distribute that power through to each term in the product. So it becomes e to the negative 2x times e to the 2x plus 1 quantity squared. And then that e to the negative 2x in the denominator will come up as an e to the 2x in the numerator. The parentheses are first. I actually don't want to do squared. I want to do m. Right. And technically, I am doing the exponent before multiplication in this case, right? All right, so remember that property. So that's why I was able to distribute that squared through. I guess technically we did. Multiply both numerator and denominator by e to the 2x. Now find all zeros of this function. You can factor out e to the negative x, right? Be left with x minus 1. This whole thing equals 0. Right, zero property. If you take the product of real numbers and get 0, then at least one of them must be 0. So e to the negative x is 0, or x minus 1 is 0. Right? E to the x can't, or e to the negative x can't be 0. Right, so since e to the negative x does not equal 0, we're left with only one option. X minus 1 has to be 0. Which means our solution is x equals 1. Are there any questions on exponential functions? Okay. Okay, continuing on. We're going to look at the logarithmic function next. No, I want to do it this way. Yes. Let start the same way I do with x with the exponential. Let b be a positive real number not equal to 1. This function is the logarithmic function base b. Y equals log base b of x. If and only if b to the y is equal to x. And so symbol is if and only if this form is known as logarithmic form. This is called exponential form. All right, so the equation on the left is known as logarithmic form. The equation on the right is exponential form. Has domain of positive real numbers. Has range of all real numbers. Has a vertical asymptote, x equals 0. Has x-intercept at 1, 0. And it has no y-intercept. If b is 10, it's called the common logarithm. And it'll typically be represented this. Right, the base 10 that's normally down here is implied. B equals E is the natural log. And it'll be represented as ln of x. Yeah, it looks about good. Okay. What we're going to do is, for these 6 problems, we're going to convert the equation into exponential form. Right? Log base 2 of 8 equals 3. Right? So we look and we go, okay, we have base 2. So that'll serve as the base of our exponential. What the log equals gives us the exponent. And then what we're taking the log of is what it equals. So the exponential form is 2 cubed equals 8. Base is 8. Exponent will be negative 2/3. And it equals a quarter. What is the base going to be here? Okay. What's our exponent going to be? One half. And of course, that's then going to equal 5. What is the base? Raised to what power? All right, b to the d equals c. Okay, when are you gonna? We're going to have 10, right? To the negative 2 equals 1 over 100. What is our base for this problem? Well, that's what I'm asking in this sense, isn't it? So what is our base? Well, that's not the base. Base E, isn't it? ln, natural log. Natural log has base E. Then the exponent. Yes, always. Natural log is always base E. The exponent would be y minus c, right? So this would be e to the y minus c. Equals x squared plus 5x minus 6. For the next 6 problems, we will do the other way, right? So we're given an equation in logarithmic form, and we're asked to write it into exponential form. Right? And so again, base is base 3. What it equals is what we're taking the log of. And then the log gives us the exponent, right? So yes, it was log of base 3. 243 is equal to 5. What is our base? Yes, it's base 6. What are we taking the log of? And then that has to equal -3. I just have to wait for technology to catch up. Perfect. Base would be 256, right? Taking the log of 64. And we get 3/4. What is our base here? Yes, log base 1/2. What are we taking the log of? And then it'll give us what? What's our base? Base U of P equals M, right? What about here? Base E. So how do we represent it? ln of what? ln of y minus c. And that equals at plus b. Now we want to go ahead and evaluate some logs. Right, the general idea is what you're taking the log of, you want to write it as a power of the base. Right, 49 is 7 squared. Then your log is the exponent, so it's just 2. $256 is what power of 4? Yep, 256, 4 to the 4th. That means this log is equal to 4, right? What is our base here? It's not 1. Your base can never be 1. Otherwise, it's a very boring function. No, it's not 1/10 either. Not 1/100. So remember, this is called the common log. So what is the common base? Base 10. That decimal is what power of 10? Yep, it's -6th power. That means our log is equal to -6. What is our base? One-ninth is what power of 27? -3 would imply it's 1/27 cubed, which is definitely not 1/9. Can't be -5. So think of it this way instead. Because we agree it's going to be a negative. Right? Because that flips it. 27 to what power is 9? Remember how powers work. Nine is less than 27, isn't it? So it can't be larger than 1. In fact, it has to be less than 1 in order to get a 9, right? Be 2/3. Cubed root of 27 is 3. 3 squared is 9. That makes our log equal to -2/3. What is our base? And 125 is what power of a 5th? Yep, -3. That makes our log equal to -3. Okay, so what I'm going to show oops, I do not want to save. I meant to clear. There we go. Okay, so how are we going to take logs on a calculator? So natural log is easy. You just look on the calculator for the button that says e to the x, and it's control that. And let's say we want to do the natural log of my favorite whole number. Just hit enter, and it's about 3.33. All right. Now, unless it's specified otherwise, we would just leave it if this was our answer as log of 28, natural log of 28. Now, what about if it's a base other than e? This is where it depends on your calculator. Right, so first off, I can also just type in ln for natural log, and then parentheses 28, and it'll give me the same thing. For the TI Inspire, gonna hit Control and then 10 to the X, which is now showing up in red. Right, and you'll see what it gives me. Now I just type in my base. Let's do the common base 10. Tab. And then what are we going to take the log of? Let's stick with 28. Can also type it in. What if I do log 28? Is that going to be 10? Okay, so if you just type in log, L-O-G, it's going to understand it to be automatically base 10. Oh, here's log base 2. Now here's the question. Do I remember the order? Okay, so it was the other way. So if you type it in, log, what you're taking the log of, comma, the base, and then enter. If you're on the 84 or 83, I think you have to go to the math menu. And it's under one of those tabs. I don't remember exactly what it is, which tab it is, because I haven't used the 83 or the 84 in a very long time. All right, but you can probably just Google it. There is another way to do it that we're going to look at when we study properties of logarithms, which I could probably start tonight and possibly even finish. But before that, are there any questions on the logarithmic function? Okay.